Graphing cubic functions. So we're going to now start looking at what cubics look like in graphic form. Of course, you've already done this in year 11, so we're going to skip over putting in certain x values and finding out what the y values are. So we're going to get straight to the shapes. So there are two types of cubic functions, both in written form and also in graphical form. So the first one is this. It looks very similar to your turning point form, except of course we've got a cubed here. So this is the form that has a point of inflection. So what that looks like is that the graph slowly approaches a stationary point. So it'll slowly approach a stationary point. It'll stop for the moment, and then it'll continue with the same gradient. So that's what this type of cubic looks like. Now this here is our point of inflection. At the moment it's at 0, 0, but in general it's at H and K. So H moves our graph left and right, and K moves our graph up and down. Of course, A is a dilation factor, which doesn't really change the shape of a graph, only just how quickly or how steeply it moves. Always remember that for H, we're going to change the sign. So it's negative here, so it becomes a positive over here. This graph will always have one x-intercept, and then the long-term behavior is dependent on the sign of A. So what we mean by that is that if A is positive, so if A is greater than 0, it'll look like this. However, if A is negative, so it is less than 0, it will look like this. So that's just a reflection in the x-axis, or you could even interpret it as a reflection in the y-axis. So the most common type of form of cubic that you're going to find looks like this. So it has several intercepts. It has more than one x-intercept. The graph is going to cut the x-axis at each of these points. So at x equals m, at x equals n, and then of course at x equals p as well. So this type of graph looks like this. It starts here and then cuts the axis with a total of 3 times. There is a circumstance, of course, when one of the x-axis intercepts, or one of the x-intercepts is repeated. So it looks like this, so x minus m all squared. So when we have this, think of like a quadratic, so squared. What this results in is a turning point. So when we have this, so x equals m, that means at that point we have a turning point. It's going to touch the axis and then turn around. So say we've got m here and m here. What's going to happen is the graph is going to touch m, turn, and then cut the axis at the other intercept. So in general, you can think about it, if the factor is to the power of 1, it cuts, and if it's to the power of 2, it turns, and if it's to the power of 3, it inflects, and that's what each of those points does. So I'll just write that out: cuts, turning point, and to the power of 3, we've got a point of inflection. This graph here is when A is greater than 0, so it's positive, but if we have A is less than 0, it'll just be a reflection in the x-axis, so it'll look like that. So for the first example, what we're going to do is we're going to sketch a cubic. In this case, you can see that it's got multiple intercepts, so it's going to be squiggly form. And when we look at our first value here, we can see that it's positive, so it's going to be our positive squiggly form. That looks like this. We can then find our x-intercepts by making y equal to 0 and using the null factor law. So we'll get x is equal to 1, positive 4, and negative 2. We can likewise find our y-intercept by making x equal to 0. So 0 minus 1 is negative 1, 0 minus 4 is negative 4, and 0 plus 2 is 2. So then we have 2 times negative 1 is negative 2, times negative 4 is positive 8, times 2 is 16. So there we have all of our intercepts. We can go ahead and graph it. We don't need to find the turning points at this stage, unless you're using a CAS calculator, in which case you should show it. So here will be 1, 0, 4, 0, negative 2, 0, and our y-intercept 0 and 16. And then you can go ahead and draw a squiggly graph in to the best of your ability. Just listed there. So this is what it looks like. That's your cubic form. Next example, again, we've got multiple x-intercepts, except we can notice that one of the x-intercepts is actually squared. So straight away we're thinking that this is going to be a turning point. So at x is equal to 1, the graph is going to touch and then turn around. But at x equals 3, the graph is going to cut. So those are our two x-intercepts. Those are when y is equal to 0, we use the null factor law. For the x-intercepts, for the y-intercept, so that means x equals 0, what we're going to do is make x equal to 0. So that'll be -1 all squared times -3. -1 all squared is +1 times -3 will be -3. So there are our key points. So again, we can go ahead and sketch that. So we have x is equal to 1 and x is equal to 3. And then our y-intercept is at -3 and 0. Okay, so just remember, here is where we have our turning point. So what's going to happen is our graph is going to approach, it's going to touch, and then it'll turn around. So it looks a little bit narrow, but still an acceptable form for cubics. All right, our final example is all about dilation. So first of all, it says use a calculator to plot the graph of f of x, where f of x is equal to this, which we'll do in a sec. And then what it wants us to do is to plot the same graph, but have these different transformations. So we're just going to quickly talk about what these transformations are, and then we're going to move to our calculator to graph it. So first of all, we can see that we have x minus 2. That means every x value we're going to subtract 2, which actually means that we are moving to the right by 2. So that is our transformation. We're going to learn in the next unit as to why it looks like subtract 2, but actually we're moving to the right by 2. Likewise, when we've got x plus 2, we're moving to the left by 2. And finally, when we've got this 3 over here, that is a dilation. Now, specifically, that's a dilation by factor 3 from the x-axis. Now, what do we mean by from the x-axis? So if we've got an axis here, from, so that means we start at the x-axis and then we're moving away from it. So actually we are multiplying each of the y values by 3. So that's what we mean by from the x-axis, because you can see we're moving vertically. Another way to say this specific transformation is parallel to the y-axis. Because you can see that this is the y-axis and then this is parallel to it. So either one works, but usually the language that we use is from the x-axis. All right, so let's go ahead to our calculator and start graphing this. What we want to do is go to the home screen. My calculator looks a little bit different on the iPad, but if you go to the home screen, we're going to go to add graphs, and then we're going to type that function. So this is what our graph looks like. What we can do is go ahead and find all of the key points. I've just zoomed in. You can use the zoom function by tapping on your axes endpoints and zooming in as much as you like. So we can go to 3 here, 5, whichever you like. All right, so let's go ahead and find our x-intercepts first. So we're going to go to analyze 0. So that's 1 point. That's another point. And our last x-intercept. We will find the turning point. So we'll go to the maximum, which also happens to be the turning point. And for the minimum. Oh, sorry, I clicked the wrong one. We'll just ignore this one. Minimum, yeah, which is this point here. All right, now I know this looks quite busy. We've got quite a few points on there. Now, what we're going to do for the first one here, it says find what f of x minus 2. So when we go to our graph, so if you just click tab, for me, I need to go to entry edit function. If we go upwards, so this is what we've typed in at the moment, so we've called it f1 of x, that's what we've defined it as. So what we can do is f2 of x, we don't need to type it out and subtract x every time. What we could do instead is go to f1, so it's already recognized it, that's how we know it's involved, of x minus 2. So that's the function x minus 2, enter. And you can see that it is exactly the same function, except all that's happened is it's moved over by 2. So for example, if we were to find one of the intercepts, so analyze graph 0, if I were to find this intercept, for example, you can see that previously it was at 1.62 and now it's at 3.62. So everything has just moved over. Now that's for part A. For part B, they want us to do something similar where we're doing +2 instead. So again, I'm going to go to F1 and this time I'm going to go x plus 2 and you can see the black graph this time. the one that's in black, has shuffled over by 2 to the left. It's the exact same graph as the blue, but it's moved over. Finally, they want us to do the same graph, but times, I think it was 2, 3. So we're going to go to function, and this time we're going to go 3 times f1 of x, enter. And what you can see is that it's dilated by a factor of 3. Now, interestingly, I know there's quite a lot going on, but try to focus on the x-intercepts. The x-intercepts are no different, because what's happening is that this dilation is multiplying every single y value by 3. So at the x-intercepts when y is 0, well, 0 times 3 is just 0. So the x-intercepts remain the same, but everything else, so for example, the turning point is 3 times what we had before. And just to kind of show that, we'll go to Analyze Graph Maximum, and we're going to choose this graph here, and let's find the turning point. You can see that it's now at 3. I know it says this number, that's pretty much a 0. I'm not quite sure why it's doing that. The negative 1.28 e to the negative 9. That means times 10 to the power negative 9, which is essentially 0. But the y-intercept, regardless, was at 1. Now it's at 3. So there you go. These are your multiple graphs. What you can do is you can sketch this into your notes if you like, or you can just make a note about which way it has moved. That there is the end of everything that you need to know for your holiday homework.